Now it is my pleasure to welcome to the stage Young-Hoo Lee and Joshua Sachs.
Okay, so let me fix this really quickly. So we're going to be talking about a lot of technical ideas today, but perhaps the greatest feat of engineering that's happened in this talk is the team that just got our slides up on the screen. So apologies for the delay, and happy to be here. Hopefully we won't have any more technical difficulties. Okay, so our talk today is entitled GPT-3 and Me, How Supercomputer-scale Neural Network Models Apply to Defensive Cybersecurity Problems. I'm Josh Sachs. I'm Chief Scientist at Sophos. I'm here with Young-Hoo Lee, Principal Research Scientist at Sophos. Just so I get a sense of the audience here, how many of you have heard of GPT-3 or know what it is? Okay, so I think almost everybody raised their hands, but I'm gonna assume not too much knowledge of the machine learning domain and GPT-3, but quickly we'll get into sort of the nuts and bolts of the work that we did here and why we think it's significant. Okay, so this is us. I'm gonna go fairly rapidly here since we lost a few minutes at the beginning of this talk. I want to just present the theses of this talk up front, and then we'll get into sort of arguing for them. So one, there's something new going on in machine learning in the last 4 or 5 years, and it really involves two components. First, we're seeing the emergence of these very large-scale models, and these models have fundamentally new capabilities, and they've been much discussed in the domain of like natural language processing, image generation. We think these new capabilities are really important for cybersecurity as well. Another new trend in machine learning is this idea of self-supervised learning, which allows machine learning models, especially large machine learning models, to take advantage of unlabeled web-scale data. I'll be talking about why I think that's important as well, and Young-Hoo will as well. Third, and this is really the punchline of our talk, machine learning has changed, and we want to provoke interest in folks coming together and looking at the way in which these changes, namely large-scale models trained in this self-supervised fashion, can impact cybersecurity in a positive way, particularly defensive cybersecurity. This talk's really early work in this space. We think we've developed some proof of concepts which are really interesting with respect to improving cybersecurity defense, but what we're really hoping for is other researchers in the community to do their own research in this area, and we're also hoping to get feedback from practitioners around how the large models we're going to be talking about in the presentation today could be efficacious relative to defensive cybersecurity problems. Okay, and also in the spirit of presenting results up front, we're going to present 2 proof of concept experiments that we did. This is almost all Young-Hoo's work. First, we're going to show that we can use GPT-3, this large supercomputer-scale neural network model, to solve the following problem. So in this example, we have a command line which is suspicious and hard to parse, has sort of high cognitive load to make sense of, even if you're used to scripting on the Windows command shell. And then on the right, we have GPT-3's translation using a method that Young-Hoo and I developed of that sort of arcane set of syntax into a lucid, human-readable natural language string. So, you can just sort of run the mental experiment yourself, like try to make sense of what's going on in this command line. This is the kind of command line that analysts at Sophos and many other places spend a lot of their day looking through to detect evidence of compromise. Clearly, it's a significant cognitive load to sort of make sense of what's going on here. And then the description is much easier to grok. The description is the command will create a file called execute.bat in the temp folder. It will then run the command dir users admin OneDrive administrators inc. and output the results to the _ output file in the local machine. The batch file will then execute itself and delete itself afterwards. So this is just one example of what we're going to show around what GPT-3 can do and how it can help in a SOC context. The second result we're going to show, and Young-Hoo's going to go into depth around this experiment, is that large models like GPT-3 can learn to detect attacks and malicious observables and spam with a tiny volume of training data. So Young-Hoo's going to talk more about this later, but what this result means here is that when we train an email detection model to distinguish between bad email and good email, we can and using older machine learning models like non-GPT, like not GPT-3 and much smaller scale models, we basically can't train a model with that scale of training data. I mean, that's a ridiculously small training set, but with GPT-3 we can achieve like a deployable accuracy. And that's significant because there are many contexts in security in which we just have a few examples of a bad thing that we're looking for, and we'd like to be able to show an AI system those examples so it could find similar bad examples. And what we found is that GPT-3 is really good at this problem. Okay, so those are like the main arguments and main results that we're going to present today. The rest of the talk is going to be a deep dive in experiments that we've done at Sophos around applying those large models to cybersecurity problems. Okay, so first some just like general background around the trends that I'm referring to in machine learning. Deep learning models are just getting bigger. Here's a really useful plot from towardsdatascience.com. Showing the growth in the size of models proposed in academic machine learning papers since really the birth of machine learning in the post-war period in like the 1950s. So on the vertical axis here, you have parameter count, which is a measure of the size of a machine learning model. And on the horizontal axis, you have publication date of machine learning research papers. And this is a log scale, so you're looking at orders of magnitude here. But so if you go back to the 1950s, you had like early neural network models with like thousands of parameters. A parameter here is like an interconnection between two artificial neurons. Going forward, you have this like log linear relationship between parameter count and time. So to all of a sudden just exploding in size. And so what happened is that researchers have become aware over the last 5 years or so that merely scaling up a neural network without changing anything else about it, say increasing the width of your neural network layers or increasing depth, but not adding any new cleverness, just merely increasing the scale, yields better results for some reason. And I'm going to deep dive into that and sort of show you guys a bunch of evidence to convince you that that's really true. But that's sort of what's happening there. Neural network models are just getting bigger. And then another thing is happening too, which is that neural network models are getting trained in a new way. Kind of classically in the deep learning space, the way we trained neural network models was if we wanted a neural network model to distinguish between malware and benignware, we gave it a bunch of labeled examples of malware and benignware. The problem with that is that there's lots of software that's in the gray area. We're not sure if it's malware or benignware. Like in our databases at Sophos, we have on the order of billions of files in our database, and many of those files we're not sure if they're good or bad. And the question is, how do we train on that data? And more broadly, there's just a ton of data out there, right? I mean, this is a plot showing the growth in sort of machine data over the last 10 years and projecting into the future. And there's just more and more data available. I mean, you can go, if you ran a web crawler today versus 20 years ago, right, you'd get much more data. Also, all sorts of digital instruments are generating data, be they in factories or cars and this kind of thing. And how do we train on that data when we don't have annotations attached to it? And what the research community has found is that there's a category of algorithms called self-supervised algorithms that allow us to train on data that's not annotated and improve our machine learning models. And the basic workflow here is that we use these self-supervised training algorithms. I'll define what they are in a minute. But we use these self-supervised training algorithms to train neural network models on unannotated, unlabeled data. And then we use our labeled data to fine-tune those neural networks to solve a specific problem, like detecting malware, or detecting cats versus dogs, or pick your classic machine learning problem. Now, how does self-supervised learning work? I'm going to give a few examples to give you guys some intuition about that. So imagine you have like a huge data set of images that you've scraped from the web. You don't know what's in the images, you don't know what they're pictures of, but you'd like your neural network model to get better thanks to those images. What you do if you're using self-supervised learning is you create a series of puzzles for your neural network to solve that are just derived from the data. So for example, a common technique goes something like this. Take an image, remove a patch of pixels from it, and then ask your neural network to predict what pixels go in that patch. And do that for lots of different images. This is my 2-year-old, so we're removing this patch here, and then asking it to predict the pixels there. here's some horses near where I live in Kansas. Remove this patch here, and then we're asking the neural network to predict this patch here. And you can do this billions upon billions. A neural network is forced to learn about the visual world, right? Because in order to predict the pixels that go in here, it needs to learn what a horse looks like, and it needs to learn that there's a horse here, and that a horse's back has a very particular shape, and that those pixels should be filled in an intuitive way, right? It needs to learn about landscapes and about background and foreground and about depth. In order to solve that pixel prediction problem, it has to learn an enormous amount of semantics about the visual world. In the following way, OpenAI, the organization that's built GPT-3, gives this model, gives the GPT-3 model like a web scale volume of text, and GPT-3 is just trained to predict the next few characters of a document. So you might give it the sentence, how self-supervised learning, and ask it to predict the next few characters, the next word, and that's the prediction target. Now again, you don't need labeled data to do this. You can just scrape lots of data, right? Hopefully get it from a source that you trust that has good information, and then just train GPT-3 to predict the next few characters. And you can see this is similar to the image problem in that in order to predict the next few characters, a model needs to have really deep intelligence about the language domain, right? If I say 55 plus 32, the neural network needs to be able to add, right, in order to predict the next few characters. And what we find is that GPT-3 does learn to do arithmetic just based on this training task of predicting the next few characters. Now, here's a final example of a self-supervised learning task. So there's lots of images on the web that have alt text attached to them in the HTML. So here's an example where I'm imagining some alt text like horses graze in a bucolic Kansas fields, a tree is in the foreground above them, a fence separates the viewer from the horses, and the grass and trees stretch into the distance. The prediction target here would be just the pixels in the whole image. So hopefully the intuition is clear around why self-supervised learning is a good idea. It allows us to take advantage of these web-scale data sets even when they don't have labels attached to them. And the result of training large neural network models in this way is that they learn a model of language or of images or of video or of audio, whatever the domain is in which you're training them. Now, here's a real example from a neural network from a research team at Google. And I'm just doing a quick time check to make sure we have enough time here. And this team trained a model on web-scale data to solve the problem I just defined, predict the pixels in the image based on a caption. So here they actually made up a caption that didn't exist in their training set, and they tested to see whether or not the model could generate an image based on the caption. So the sentence is a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign on its chest that says, "Welcome, friends." So this is such a wild caption that it's highly unlikely this image actually exists in the wild, and in fact, this is the creation of some researchers at Google. Now, when they asked their models to generate the resulting image, this is what they got with a very large model that had 350 million parameters. So 350 million floating point values that define the interconnections between the artificial neurons and the neural network. And this is already an impressive result, right? There's an animal that's vaguely kangaroo-ish. There's something that's sort of vaguely Sydney Opera House-like. This is a sort of fabric that approximates a hoodie. You're not really getting the characters, but you do get a sign with some gestures of letters here. So it's already quite incredible that an AI model can generate this image. But I want to demonstrate what happens when you scale these neural network models up without changing anything else, when you just make them bigger with no new clever mathy ideas. What happens when you scale the model up to 3 billion parameters is you get a kangaroo now. And you get something that's much closer to a hoodie. And you even get the neural network learning a little bit about how to write letters in the visual domain. So it's not quite getting welcome friend, and it's adding some weird sign down here, but it's getting closer. And when you get up to 20 billion parameters, the model's able to actually understand the relationship between text and imagery. So it's learned to write in this case, right? Even though the researchers didn't explicitly train it to learn to inscribe natural language text into the image. It's learned what a hoodie looks like. It's got the blue sunglasses, the Sydney Opera House. Young-Hu, who's from Australia, could tell me if this is exactly correct, but at least it's close and it's recognizable. So there's this magic thing that happens when you combine self-supervised training with very, very large-scale models. And to be clear, a 20 billion parameter model would need to run in like a room-scale supercomputer with like a ton of GPUs and take a ton of energy. So it's not easy to create such models. But it's pretty magical what happens when you get into this sort of large model, self-supervised learning regime. There's lots of examples of this that you can find if you look up the Google for.We'll paper, which is where these images are from. You can see lots of examples from their work. But here's an example of the results from the models of these different scales when prompted. A map of the United States made out of sushi. It is on a table next to a glass of red wine. You can see, it doesn't get it with the small model. With the large model, it really does. And again, just look up Google and for.We'll if you want more examples of this model. Now, let's get down to GPT-3, which is the model that we're using to do the research that we're going to present today. So GPT-3 was trained on text to predict the next few characters in a document. But what it's learned to do is, for example, create valid Python code. So here I prompted GPT-3 with the prompts compute mean and standard deviation, and then I give it a doc string, compute mean and standard deviation of the input data in pure Python, and render the result in flashy HTML on a page titled Don't Trust Summary Statistics. Then if you just ask it to autocomplete, it actually generates valid code that does both those things and composes those concepts together. So you can see how this is analogous to the image example. So here we asked it to do two things: compute some summary statistics from sort of Stats 101, and then render that stuff in HTML. And it sort of knows about summary statistics, knows about HTML, and also knows how to sort of knit those concepts together into a valid Python function that actually works. And to be clear, like our role here is we are using OpenAI's models through their API that they gave us access to as researchers, and we're building on top of GPT-3, and you'll see how we've done that for security use cases in Young-Hu's portion of the talk. Now, so this magic thing that happens when we scale neural networks up and train them in this self-supervised fashion is that there's like this really clean relationship between model scale and reduction in model error. So what you're seeing here, I mean, I can go into the details, but basically the punchline is a team at OpenAI published this classic paper where they showed that as they scale up the size of a model in terms of like orders of magnitude of interconnections between artificial neurons, there's this smooth decline in the error rate of those models, which is a really remarkable, I would say it's a key result in machine learning that's come out of the last like 5 years of machine learning research. Now, why does this matter for security? The size of today's security data science models falls in this kind of size range. So our day job at Sophos is to operate about 40 machine learning product integrations within Sophos's like firewall product, endpoint security product, mobile security, email security. We do a lot of machine learning at Sophos, and we are using machine learning in almost all of our detection pipelines within our company's products. But the models that we've deployed all fall in this kind of size band in the distribution of model sizes. We haven't yet, and I know my colleagues at other companies, as far as I know anyways, haven't yet explored what happens when we scale security models. So not natural language, not computer vision, but models that like detect bad stuff that help SOC analysts. When we haven't experimented yet with scaling security models up to this kind of size range that we're seeing in the broader machine learning community. Now, the presentation we're making today is the result of our early experiments in applying these very large models to security problems. We think it's really important that researchers in our community, in like the security data science world, go in this direction. And so again, like we're hoping that other folks follow up and do even more impressive stuff with large-scale models. So before, I'm about to hand it off to Young-Hu, but before I do that, I just want to give a little bit more intuition as to why these large models may matter for security. So one of the models that we use at Sophos is a model that looks at a domain and decides what content category it falls in. Like we have like K through 12 school customers that don't want kids looking at certain categories of content and this kind of thing. And so this is one of the things that we do on our team. We train our domain content classification model on like tens of millions of examples. And we need to. It's a small model and it needs to be trained on a lot of data. We did a quick experiment with GPT-3 to see how well it could categorize domains into content categories using just 5 training examples. And it did a really good job. It sort of definitely blew me away when I saw this result. So here I just show GPT-3 a prompt. I show it berkeley.edu maps to education, Amazon maps to shopping, et cetera. And then I show it a new domain that it hasn't seen before, shootingrange.com, and it just knows to autocomplete that as weapons. In a malware detection context, if we're trying to detect, say, like phishing domains, we can give it like 4 examples of like definitely a phishing domain here. I mean, I just made this up, but but it looks like a phishing domain. PayPal customer support blah 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 .ac.uk. Some good domains, another bad one, and then it nails it when I give it a new phishing domain. So again, an example of like the phenomenon where GPT-3, because it's been trained on like the entire web of data, it's learned some syntax and semantics around language, and it's able to see that, oh, what's going on here is categorizing sites into good and bad, and it's sort of queuing off of all of the knowledge it learned in that self-supervised training context, and very quickly learning to do what we're asking it to do in this context. And this is significant because, like, in the future, as people start to use these large models in like a SOC context, if you're seeing a certain type of thing and you want to go find that thing in all your data, you can imagine writing a little prompt like this, and then pointing GPT-3 at a bunch of data and having it find examples that you're looking for in a much more intelligent way than today's machine learning models that are a smaller scale. We're going to be talking about 2 different ways of using GPT-3 today. One is prompting, which I just showed, where we just show it a prompt, ask it to autocomplete, and get an answer out of GPT-3. The other involves backpropagation and stochastic gradient descent. For data scientists in the room, this is just the standard way that you optimize neural networks. That's called fine-tuning, and what we do in fine-tuning is we adjust the interconnection values between the neurons just a little bit more beyond what they were when we finished self-supervised training a model like GPT-3 in order to solve a problem like spam detection or malicious URL detection. Okay, so this is the last slide in my section here. Hopefully I've whet your appetite into thinking about how these large models may apply in security. I think you can probably think about some offensive applications of these models. We're thinking in this talk about defensive applications. We've tried a bunch of things. Young-Hoo's done a bunch of work in building a natural language user interface where the user types in like show me all network connections that are open from Windows machines outgoing to China, and that gets translated into a database query. We think this is useful for detection. You'll see the results that we have around using this for reverse engineering, but we think there's lots of other applications as well. Okay, and with that, I will pass it off to Young-Hoo.
Thank you, Josh. The kangaroo image was very impressive to me, who just came from Australia. Yeah, it is great to see those Australian animals and the building here again. In the second part of our talk, I will be talking about how we can create 2 cybersecurity applications using a large-scale language model. We will be using OpenAI GPT-3 as our large language model. So the model is so large, you can directly use it unless you have a supercomputer. Fortunately, we can access the model now through the OpenAI's API. So our first application is a spam detector. When you start a new ML project, probably you will be starting with few examples. And also, we just collect a few new spam messages, but we are going to detect those similar ones. When we train a small traditional models, you will be required to collect a large set of training data to train a new classification problem. It is something like when you train a small puppy, probably you need to show him many examples. However, a smart dog with a lot of experience will quickly learn with few examples, and our smart GPT-3 can do the same job. So this is our performance of spam detection. GPT-3 with only 1 ham and 1 spam achieved impressive result of detection rate of 90%. With 8 samples, even better, we got 95 accuracy. On the other hand, traditional random forest model only got about 55%, which is slightly better than random guessing. We will talk about how can achieve this impressive result. And these are our evaluation data and the model settings. So teaching GPT-3 to solve a prediction problem can be as simple as designing a prompt so GPT-3 can autocomplete the remaining part. For example, converting movie titles into emoji icons is quite simple. So we just provide 3 examples here. Back to the Future with some relevant icons and Batman and Transformers. And then we ask about our question, Star Wars. And then we get impressive result, so the relevant icon. This is how we can provide the data to the model to autocomplete the remaining part. So now let's design our prompt for our problem. So we start with a simple instruction, which is classify the message as spam or ham. And then we provide some examples. So we select one spam and another one from ham. And then we add our question sample, pre-taught ringtone. So with this input, GPT-3 can generate the spam as output. So GPT-3 is a pre-trained language model. It has been pre-trained to predict the next word. So GPT-3 can generate the most likely the spam as output. So let me show you some other examples. So from the previous examples, so now we can test new samples. For example, urgent, your mobile number has been awarded. This one is definitely spam, and it's correctly identified as spam. And another one, yes, I'm in office, it's detected ham correctly. So actually, this is a screenshot from the OpenAI's playground website, where we can test our input and output with some settings. Here, one important setting is the model we set as a text Da Vinci. This is the largest GPT-3 model for text generation version. So our application, the first application, show GPT-3 with Fuchsia learning is a powerful tool to generate a classification problem. So the second application is generating human-readable explanation of malicious command lines. The SOC analyst analyze thousands of malicious commands every day, and it is a really hard and time-consuming job. And as you can see, this is one of the malicious commands. So it is really long and it's hard to parse. So our question is, can large language models can make this job easier by describing this command in simple language? So yes, it is possible. So from the command, we can generate human-readable description. This is actually the description we generate from the model. So the description said the command will create a file called ex.bat file, and it will execute and delete afterward. So it is one of the malicious behaviors, but we can actually recognize from the description. So let me show you how we can achieve this one. Actually, GPT-3 reported 2 types of different models from OpenAI. The first one is text generating version. So we just use the text generating version for our spam data. And the second version is code generation version called the Codex. So the Codex models has been pre-trained with many open source projects from the GitHub. So it can write code in many different languages, including JavaScript, Python, and shell script as well. So this is our choice for our second use case. So let's design our prompt. So we have 2 sections. The first one, we provide a command. And the second section is for description. So this will guide GPT-3 to autocomplete the remaining part. So let's have a look at the result. So now we have the description from the command. So the command will copy the binary into a temp folder. So it generates a valid description from the command. However, the command is malicious because it copies the binary from the system folder to a temp folder as .exe. So it is a malicious activity. However, our description did not point out the malicious part. So we needed to improve the quality. And our approach is we needed to provide some additional context information. Usually, the suspicious command can be detected by signature-based rules. So we can use Yara rules or Sigma rules. So in this case, the previous command actually detected by one of Sigma rules, and the signature was Windows suspicious copy system 32. So we can use some additional information from the signatures. So this is the second version of a prompt. So we use the same command, but we add additional tag section because one command can be detected by multiple signatures. So we can add all the signatures in tag section. So now we get a better description. As you can see, now the description says the command will copy the binary to a temporal address, so where the attackers can use the binary to perform malicious activity. So now it described the command correctly and also mentioned about the malicious behavior as well. So now we have the better description. However, we wanted to improve further from here. So what we can do is actually, if we look at the settings, we set the model as the code. This is one of the codex model. And then also we can change the templates from 0.7 to 0.8, or we can also change the top probability. So with these settings from the same input, we can generate multiple descriptions, and then we can select the best one. So our approach to select the best description is back translation. So in natural language translation task, for example, translation from English to French, it is not easy to evaluate the output of French. But if we translate the French to English, now it's clear we can compare the original English to back translate version. So we can apply the same mechanism for our second case. So the command is one language, and description is another language. So we can actually generate the command from the description. So now we have the command and the back-translated command. So we can easily compare the similarity between the original one and back-translated version. So let's have a look at these are the overall steps. So in step one, we will generate multiple descriptions from the command and tags. In second step, we can generate the commands from the previous generated ones. In the last step, we can rank the descriptions by similarity scores between the original command and the back-translated ones. So this is our new prompt for the second step, back-translation step. So we provided the tag and the description, and then we ask model to complete the remaining command. So this way, we can regenerate the previous command. So if the command is describing the original command correctly, we will be able to reconstruct the command. So let me show you the two examples of descriptions. We generated these two descriptions from the previous command. So the first one actually did not correctly mention the binary name, but it just mentioned temp. So it failed to reconstruct the previous command. However, the second description correctly construct the previous one because it has the correct file name. So our back translation method can be used to improve the description further. So this is another example. So the command is, maybe if you are not familiar with this one, it's not easy to understand. However, our description says the command will search the files on the desktop folder and the server folder, and will find the file containing the password. Actually, it is finding your password from the desktop. So our source code is available in our GitHub repositories, and it includes our two applications, the spam detect and the command analyze. So in summary, GPT-3 with future learning is so flexible and powerful. You can easily create powerful applications. The title of our talk is GPT-3 and me. So it was our successful story, and it's time for you to create your applications. That will be your GPT-3 and you. Thank you for listening. It's time for Q&A.